So let's see, even the camera seems to be right angle because the last week I didn't set up the camera to be facing me, so there is a video without my presence, which I don't mind, but it looks a bit dead if there is just some voice talking. What we went through last time, we saw that our world is rich of data. We might already know, or we also try to point it out, that this data is not always reliable. There is always some noise in the measurements. You saw it in many of your lab exercises, and the question is how we are going to deal with this situation. How are we gonna make sense of the data which are having some troubles, where the values of these data are slightly off because there was something. Sometimes it's a systematic error. You heard it in your in many of your lab exercises. Yeah, something is off. Somebody didn't calibrate a device, and there is like standard error of the which comes from many sources. Small errors would accumulate and will actually give you some measurement noise. And at the end, we should be able to make some sense of the data in terms of finding a model, finding some function, some kind of algorithm that will make sense of this data, despite that there are some problems, for example, with the noises. So this is what data-based modeling is about. Part of the database modeling is system identification. That's where the title of our course come from, where system identification is more when we are talking about the dynamic systems. We will not start right away with the dynamic systems. We will slowly move into that. So this is what we already discussed in our modeling in process industry class. This was actually the types of models that we built, so-called first principles models. So the models are coming from the principles of physics. Yeah, so that's what gives this name, and so those are the models which are based on the physics. In our world, for this course, we will be in the world of the database models, and we will see some static and dynamic models, how we can find them, how we can even look at some linear or non-linear models. Some very little about the state estimation, which of course is some technique that tries to process the data, remove some noise maybe. Okay, so let's jump in, and now I will surprise that I have a Slovak slide. Hope this works well. So this is the set of slides that I didn't specifically prepare for this lecture. I prepared it for some lecture. What is it? The Researchers' Nights, European Researchers' Night that usually is around September. So it was prepared actually for school kids to show them a bit of the probability, show them how it works. And our question for today would be how we can really model the noise in the data. How can we model that we have some uncertainty in the data? How can we make sense of the data before even building some model? And one of the ways is to understand the probability and do some statistics. Let's try to dwell into that. maybe if we have time, I was yesterday at the there was probably you saw it at the electrical engineering faculty. There was this Slovak researcher Michal Valko, who is one of the founders of the Google DeepMind, and well, really a top scientist. And well, he was talking about the LLMs, large language models. You might think, what does this have to do? Well, everything. LLMs are just applied statistics. What they present in many equations with some mean values, some standard deviations, probability. This is how ChatGPT is trained. And yeah, if we have time, I will even tell you. We will see what we could do if we can train multiple times ChatGPT. We could even make it to give us like a confidence in the answers. This is the big problem, that you get the output from ChatGPT, but nobody is telling you like this output is 80% confident to be correct. This output is only 20% confident to be correct. That's a big problem now. So on the way there, what's a probability? Well, there is some simple definition. What am I doing wrong here? So probability, we know this from high school. It tries to express that some event can happen with a certain likelihood. So it expresses the possibility in some mathematical terms from 0 to 1. Yeah, we know this. And one of the best testing devices is a dice. So let's try some experiment. We saw a visualization of the data last week. We looked at the case of histogram. So here we will be building a histogram. The histogram will be telling us what? We will basically see whether we get 1, 2, 3, 4, 5, or 6 on the dice. Actually, if you want, you can make a physical experiment with this, if this dice works. Okay, so 1, 2, 3. Please, you can try doing your own experiments. Just give it give it a try. So, Hannah, which number would you roll? Roll it. Yeah, that was number 2. Let's see what our experiment does. So, 1. Okay. Okay. What happened? Is it likely or not likely? Okay. 2 again. Yeah. Okay. What happens? One would say that the statistics is getting off. 6. Okay. 5. Okay. Well, it's getting there. So that wasn't a proper rolling. Yeah. Okay. 5. Very good. Okay. So what we are witnessing? Why, for example, we didn't see number 3 or number 4? Is there a problem with the dice?
The number of experiments is not sufficient.
Yeah.
There's like big numbers, log or something like that. If we try to roll it infinite time, it should be equal.
Exactly. Yeah. We'll see that. We will not throw the dice. We can go up to 6 millions in this slide. So 6 millions would take us a lot of time and a lot of memory. Well, because it would be hard to keep it in our heads. Yeah, Michael said it also right. What if the dice is unfair? Yeah, if it's unfair, then there will be some problems in our histogram. We would try to see some numbers are occurring more frequent than the others. But really, well, we cannot say from the small amount of experiments. So here we will see couple of experiments. On the top, we are actually even counting how many times we threw a dice, and this is, I promise, this is done with a fair dice because it's simulated in MATLAB. Yeah, I didn't sit in my office and throw the dice for 6 million times. We will see. Okay, but yeah, let's see. So similar to our dice so far is the response of MATLAB. So 5, 6 exactly once. There is 1, there is 6, there is 4 coming, and more I'm throwing. Let's say, let's keep it until 20. Yeah. Now, so even with the 100% fair dice, like same person is throwing the same dice, we get this result pretty easily. Yeah, in 20 attempts. So it might seem, well, okay, this dice is maybe throwing only the number 6, well, almost in half of the cases. Yeah, some games where throwing the 6 is the best result. Might be easier with this one. So if we have a MATLAB and we can simulate this, so what do we do? We get more attempts. Yeah. So if we get 100 attempts, it's already quite a different picture. Yeah, right. It doesn't seem that the 6 is dominant. Now the 5 seems to be dominant, but not really. Yeah, only relatively slightly. Let's now try to do some exponential growth of the attempts. So let's go to 1000. So these small bar here, that's the result from our previous attempt. Yeah. So if we had 100 of trials, then they are still kept here as a reminder what happened before when we only had 100 attempts. So 1000, it's still, does it look like we expect already or not? No. Which one is off? How would you calculate it? What do we expect? How would you now calculate the probability that we throw 6 on the dice?
The wanted outcome divided by all the possibilities.
Mm-hmm. Which would here be roughly if you read the graph and put it to numbers. So the number of successful attempts versus the number of all the attempts. So roughly, yeah, for 6. Let's say 140 divided by 1000. Yeah, so it's getting close to 1/6. How much is 1/6? 1/5 is 0.2. Yeah, so it should be something smaller. Let's see what happens once we roll more. Roll more means now we have 10,000. So here is still the 1000 histogram. There is the 10,000 attempt. Sorry, there is 100 attempts histogram, 1000 attempts histogram. Now we have a 10,000, and yeah, the columns are getting evened out as we would expect. Now we go to 100,000. They are really equalizing. Million. not bad, and such that our math is easy. Let's just do 6 million attempts, and with the 6 million attempts, where do we land? Well, we actually start to see quite nicely that each of our numbers on the dice is equally likely, and we get 1 million ones, 1 million twos, 1 million threes if we are throwing the dice 6 million times. So at this point, we of course conclude what? That we can make this histogram somehow normalize it, such that, well, we don't care about the absolute numbers, but we care about the proportionality, about the ratios. So this would mean yeah, we have the 1/6 here, and then we can say, well, we calculate the probability of an event of throwing 3 on the dice, 6 on the dice, as the number of successful times when we throw, for example, 3, and we divide it by the number of attempts. This is, I guess, pretty clear from the high school, from everything before you even saw. Yeah. So now let's make a standard detour, and this is, I don't know whether you saw this. This is a standard example when we will be continuing with this dice game. But now let's say that we will throw 2 dice at the same time, and we will not be interested in the individual numbers, but in the sum. Yeah. So how much do our do our numbers sum to? Yeah. So this will be number 12. If we have just 1 dice, we would see basically this outcome, because yeah, we will be just summing this one. So what would change? What would we expect? How will it look like? Maybe somebody who saw this example before. Should we
probably turn into something like Gaussian curve, or it will look something like that, because the numbers 6 or 7 are probably like most likely with the sum of them.
Sounds good. Sounds good. Yeah, because what we have these possibilities. Yeah, if we just without throwing any dices, if we just again do the same trick, number of successful attempts versus the number of attempts. So we have how many? So this is rolling 1 dice, this is rolling another dice, so 6 possible outcomes. We have 36 possible outcomes for the sum on the 2. But as Adam is mentioning it, well, if we look now at the frequency, if we try to make some kind of a histogram, well, 3, for example, is here only twice, but 7. Yeah, that dominates, because we have 6 plus 1 and 5 plus 2 and 4 plus 3 and so on and so forth. So this game is already changing, and we don't have no longer have this nice uniform probability. Our model of this game would actually look something like this, and this will be exactly this number of attempts, the histogram of how we play the game, and the number 7 would be most likely is the one which comes most often. The Gaussian curve, not yet. Tell me. Okay, good. So we are not yet at the Gaussian curve, but we can get there pretty easily. What if we now change our game, and instead of 2 dice, we throw 3 dice. So it's not, we cannot longer don't know whether to say that 10 or 11 is the most likely one. So what would change? Yeah, the lowest possible outcome is when we get 1 1 1 on each on the 3 dices. Yeah, and the highest possible is 6 6 6. So we get 18, and again this 3 and 4 and 5 and 2, that gives us the sum of 10 and 11. So let's now continue this game, that we will take more and more dice and throw. So this is the game with the 4 dice. This is the game with 5. This is the game with 6. We start to see that something is appearing. Some shape is appearing. 7 dice, 8 dice, 9, 10. How long do we continue? 11. Already the bins are, or the range on the horizontal axis is so large that these bins become smaller, and in the visualization, yeah, the width of them. And if we continue, I think the number 20, so would be a good one to stop, because when we were throwing 2 dices, we had the 7, number 7, as the most probable outcome. Well, now we have 10 times more dices, so we have number 70 as probably the highest peak here. Yeah. Also, the visualization is maybe not perfect, or the number of atoms wasn't enough. Yeah, and this sort of a curve is already reminding us of something, and this something was even what Germans used to put on their currency. Yeah, so Germans, they put mass in the center of the 10 mark bill. So this bell curve, even with the equation known as a Gaussian curve, and of course they are celebrating the best mathematicians probably to ever live so far, Carl Friedrich Gauss. Okay, so if Germans had this on their money, on their notes, we should probably have a look at what this function does. Yeah, we will rewrite it and have some fun with that function today. So our function, the bell curve, is a so-called probability density function, and it's a long name, but a good abbreviation for that is to write PDF. Yeah, sounds already something sounds familiar, but it's not the portable document format, but it's probability density function. How is this in Slovak? How do you remember? So now we will have a bit of the terms that come in this probability realm, and it's also good to know the Slovak alternatives. Do you particularly recall how these functions were called? Okay, it's not yet the Gaussian curve. It can be now any. So probability density function would be we can even how do I move? Okay, wow, no. we can get a probability density function even for the so-called, come here, even for the so-called uniform distribution, and it won't be the function with e to the power of something and so on. So in Slovak, and maybe you haven't heard it, so the just put it like this. Slovak ekvivalent pravdepodobnostná funkcia. Pravdepodobnostná. I would say that I like more the probability density function. You will see why. It will basically, as the function name says, it will tell us some likeliness of an event occurring with the dice when we have only 6 possible outcomes. That one is easy to interpret with, for example, temperature in this room, where we can measure really in the continuous domain. That's already kind of hard to tell, like what is the probability of the measuring the temperature 25.72784, you name it, whatever number of decimal places. So it's this concept of saying, throwing a 3 or 1 on the dice is 1/6 is a bit distorted, but don't worry, there will be a way how to go about it. So then let's say like something like a definition. An event would obey, and now we go for the normal or Gaussian. Those two are really synonyms. Normal or Gaussian distribution. So normal distribution, Gaussian distribution. Whoever talks about it, maybe if Germans talk about it, they would put the word Gauss. If somebody non-German talks about it, they would use the word normal. So then we say some event X has this normal distribution. So the capital X would be something which we call a random variable. So capital X is a random variable, náhodná premenná in Slovak, and this tilde sign should basically say what is written in this even would obey distribution. In these words, and the n should be standing there for normal. The whole world, even the Germans, write capital N and not G. So the normal distribution would then be defined with some mu and with some sigma functions. Do you recall the mu's and sigmas from the high school? Maybe sometimes you use some instead of mu you use the notation x bar. Even in Slovak, shouted at me, what are these? Yeah, or well, let's call it mean. That would be the better. Yeah, English is not that cool in distinguishing mean and average. We'll make sense of it. So the two let's call it parameters are mu, some people like call it x bar, which is the mean, and or mean value, and I like the English literature also call it expected value. Which is quite nice wording. They would even write it like mu is this kind of e over x. So if my data are distributed according to the normal distribution, I expect the event x. If it is throwing a dice, measuring temperature in this room, calculating what will be my likely result at the next exam, then the expected value will be this number. So this here is still kind of abstract thing, because it's a random variable. There is still this uncertainty. This here is already making sense. Like, what can we expect? What can we expect from our dice game? Well, we could already calculate. Oh, let's take this simple example. Our mean would be actually the number 7 here. That would be the most expected, the expected one. And so what's the Slovak word? We call it stredná hodnota. That's the word, yeah. So Slovak stredná hodnota. You heard that, yes? No? Good. The second mysterious term, and maybe a note, there is usually this notation. People would use either sigma square or sigma. We'll see what is the difference. So sigma is something which we would call, that's the standard deviation. In Slovak, what would you say? Štandardná odchýlka. Exactly, yeah. Some people do like half translation, like štandardná odchýlka. Some people do the full translation. Smerodajná odchýlka. Okay. We'll see in a second what it does, and if we should use sigma square, this in English would be called variance. We will talk a lot about the variance. It's a very helpful concept, and in Slovak this is rozptyl. You recall this. You recall this very good. All right. So let's now try to do not go to any more terminology and terms. Let's see what this function from the German note would tell us and might tell us. So we have 1 over, there is this sigma, square root of 2 pi. Interesting, we'll see why it's there. And we have the e exponential to the minus x minus mu squared divided by 2 times sigma square. So this PDF of x, where I try to now write lowercase x, which is the outcome of an event. So this is going to tell us how proportionally likely is the value of x is the value of x, is the outcome x. 1 over sigma square root of 2 pi e to the minus, and there was a fraction x minus mu squared divided by 2 sigma squared. Kind of complicated function to even look at. Yeah, it's scary. I give you that. Let's try to break it into smaller terms, or let's even try to have a look at the simpler function. Let's maybe try to have a look at the function where mu will be equal to 0 and this sigma will be equal to 1. Somebody would call this situation, if we have these two parameters, if we, for example, now write that our temperature measurement in the room obeys standard or Gaussian, normal or Gaussian distribution with mean 0 and standard deviation 1, then we are talking about the standard Gaussian distribution or standard normal distribution. Standard normal distribution. Good. So in this case, our function would look like this: square root of 2 pi e to the what remains there, like 1/2 minus 1/2 x squared. Right, if I plug in the mu and sigma. Good. So let's just plot it now, but we can, for example, do what? We definitely know the function x squared, right? So let's try it. I wanna have like 3 graphs beside each other. If you are making notes, that's what you might also wanna have. Well, function x squared. How does it look like? Yeah, exactly. So we have value of 0 at some point. At some point 0, which happens to be our mean, our x squared function looks like this. Maybe I make it a bit leaner, because a bit later I wanna plot slightly wider version of it. Okay. So what would happen now if we make this function negative? So minus x squared, what would change? How would the picture look like?
It's concave.
Yeah, it's concave, exactly. And now this 0 here will move as the maximum. Yeah, you already saw this. Good. And now but again we have this maximum at this mean. Now the last step. How do we apply? How do we apply this exponential transformation? The 1/2 won't be a problem. We are just sketching it. The 1/2 is only telling us how fast this goes to the negative infinity or to the negative values. But how would the shape change? Exponential function with quadratic. Okay. So what do we? This function.
It should still look like the basic exponential function, I believe.
Yes.
And we can say that if the exponent is equal to 1, it's gonna be e.
Mm-hmm. Yeah. Continue on this line of thought. And if exponent is equal to, that's what we are more after.
If the exponent is equal to 1, so
no, we don't care about 1. If the exponent is equal to, tries to find some other number.
Oh, 0.
Good. What happens then?
Then it's gonna be 1 on the axis.
And that's so. What will the exponential function is increasing, right? So if we have a maximum of this function at point 0, will this remain to be maximum? Yes, it will. Now I'm thinking whether you've done this transformation in the optimization class, because sometimes you can take like a logarithm, which is also increasing function. But okay, let's.
How the original function looks?
Which original one?
The one we want to get in the end. The
Parabola? Ah. Well, that's it. Let's just. Exactly. Ah no. Good thinking. Yeah. If we are trying to draw a Gaussian curve, we will draw a Gaussian curve. Okay. So let's do it point by point. So at the point 0. We get what? X squared minus times minus 1/2 will still be a 0. E to the 0 will be 1. And now, so our values. So how does this exponential? No. So the exponential function. Yeah, we all know it. We all have seen it. Some specific points. Well, our minus x squared only takes negative values, so we will be only in this part of the graph, and our values will be at maximum 1, and at minimum they will tend to 0. Exactly. So that's the transformation. Yeah, our seemingly infinite tails here they would transform, they would curve such that we'll get a minimum, or let's say better say infimum, yeah, because it's not anything that we can reach. Everybody cool with that? At your exercises you will you will try to plot this. You will generate some data to plot this. So you will play with that. So if this is a probability density function, it's so it's not a probability itself yet. What would and why is there, since we already started with it, why is this funny 1 over square root of 2 pi there? What's gonna happen if I take our dice distribution? Where is that? Maybe let's take the one with the, where is the one with the numbers? Will it start from the, no, perfect. So if I now calculate what is the probability of throwing 1, 2, 3, 4, 5, or 6 on the dice, how would I proceed? Or let's do it the other way around. Try thinking about one of the questions that we might have here. Like how likely is it that I throw this and that? I don't wanna put anything into your mouth, but try to think about the questions that you were trying to find answers when you saw this previously. What can we ask? We can ask, for example, how likely is it that I throw an even number? Yeah, 2, 4, 6. And how do we calculate that? Or how is it? What's the likelihood? What's the probability that I throw an even number?
50%.
Mm-hmm. How can we get it from here?
Because every possibility has the same probability, and half of all possible numbers are even.
Okay, if I make it harder, so okay, so if I say that you throw 1 or 6, then you would say it's a 1/3 of the cases, so it will be 0.333, right?
Positive outcomes divided by total possible outcomes.
Yes, but well, we already have it here. We already have the model. But what we can actually do, we can now use these individual probabilities of the successful events occurring, and we can make what's the word? Not združená pravděpodobnost, not joint probability, but well, I can recall the word not in Slovak, not in English, but no, I know how to write it mathematically, but I. Yes, we can just sum. So if we have or event, so we can just sum the probability of 2, sum the probability of 4, sum the probability of 6. 1 6 1 6 1 6 together 3 6 1/2. That's the probability of throwing an even number. We can ask different questions, and this is already harder. What is the probability that I throw 1 twice in a row? What is the probability that Hannah threw? Yeah, there is a multiplication, and that's a joint probability. We will see it. So if I take the probability of the event 1, and what we actually have here is the probability density of the event that I throw 1 on the dice, and we process it. So what is the probability of throwing 1, 2, 1 or 2 or 3 or 4 or 5 or 6?
Certain.
Yeah, good. That's what. So 1, and we would get it as 1 6 1 6 1 6 1 6. Yeah, 6 times 1 6. So it. What we have done now, we went through all the possibilities and we summed all the probabilities of the different events for the dice example, and we got 1. That means that if this function should be similar representation of a probability of some event, then it should have the same property. That if we go through all the possible
We can somehow, I would do it like, we would take this curve and would divide it into like 6 compartments.
No, it's not possible. It's not divisible. It's continuous.
Coefficient before the function. So when we integrate the function, we'll get 1.
Exactly. So our probability density function and each probability density function, even the uniform one with the dices, we saw it. We went through all the discrete events, 1 2 3 4 1 6 1 6 1 1 6 plus 1 6 plus 1 6, and we get the number 1. So we should be able to do the same thing with the probability density function. If we integrate this function e to the minus 1/2 x squared, we should get 1. Let's test our good old friend MATLAB, and this is now particularly challenging to do MATLAB on a tablet, but well, let's try. I did some preparation, otherwise it would take so long. Let's say that we have, let's maybe start almost from scratch. Copy. Let's define, what is this? Disconnected. Okay. I shouldn't have tapped it. Okay, I don't care. Let's see. Hopefully it still works. Ah, no, it needs to connect. Good. So what we do? We try defining our function. Familiar with this kind of notation? Have you? Okay. Maybe not everybody, but this is how we can have fun with the. So you don't need to always write the function. If it's just one line of code in MATLAB, you can define it through this function handle. And let's now do the integral of this function. Come on, copy. So we take integral of the function fun from minus infinity to infinity. Why is it not 1? Can we help it?
Because the coefficient, like the square 2 times. Exactly.
So what if I take square root of 2 pi? And you already see the answer, but just to see that I'm not cheating here. Yeah, we get exactly the same number, 2.5, and so on. So if we take integral this function, we get 2.5 and something, and in order to obey this property, that we need to be certain if some of the events must happen. So either the temperature is minus infinity in this room, or is some reasonable finite number, or is plus infinity. It has to happen. Yeah. So that's why there needs to be a probability of 1, and this is the magical constant. So this is the 2.5 something. Good. It somehow works mathematically, but we still haven't made it to the point where we can now ask the reasonable questions. Let's say. Unfortunately, we need another function for this, but I promise this is the last one for today, and this is the function with which we will calculate not probability density but the probability itself. And this function is called cumulative density function. No, sorry, cumulative distribution. Too much talking about density. Since we before had PDF, now we have CDF. And the Slovak term, this one is nice. Slovak term is distribučná funkcia. How it goes notation-wise? So if we compare now the PDF and CDF, it's even a good habit to say, like, if our PDF would be we didn't call it any function name, but we can give it like our fun in MATLAB. We can call it like fx. We can call the sister function of the PDF, which will be CDF. We can write it with capital F. And well, this is just the notation, but the real meaning, this is really telling. The PDF is only telling us about the density, let's say relative probability, but the CDF will tell us the probability itself. Yeah, so PR for probability. And we have already saw one example of the CDF. Actually, at this point, you shouldn't be surprised that, well, we calculated what is the probability that x will take a value between -infinity and infinity. Here our distribution function. Let's change a variable slightly, such that I promise it's helpful. So the value of the distribution function of a particular x. So the z will be a value of x. I will draw it in a second. It tells the probability that x is less or equal z. And the integral, you know, it's, let's say, a mathematical definition, and in order to somehow work generally, it's defined like, well, we need to start at one end. So we pick -infinity. That's the end when we start, and we can calculate now probability. So what is the probability that x takes value between -infinity and z? So what is the probability that the temperature in this room now is below -5 degrees. Yeah, we would calculate the integral from our previous measurements and the modeling. We would probably find out that it's 0 because it's usually heating up here. So this is where we take our PDF, we plug in x, and we integrate with respect to x. Let's try plotting it. So if our PDF would look like this, and now I on purpose already try to center this this graph, this axis on the mean, where if we have the Gaussian distribution, well, it's the same picture as we have on the right. Well, this function would look like something like this. The last one is probably okay. It would tend to zeros at -infinity and +infinity. And now we will construct our CDF function, and let's say there will be the mean will be here, and let's now pick. So our z is some value of x, so we can pick z anywhere, really. Let's get some nice color. Let's pick, that wasn't the color I meant. Let's pick z here. Let's call it like this is our z1. So what we are doing now, if we are asking what is the probability that the value of x will be below z1. Yeah, if this is a temperature, I pick 10 degrees in this room. So between -infinity and 10, what's the probability? Well, we can only find by doing the integral. We calculate our area under the curve. It's the same principle as when we were counting up the 1, 6, 1, 6, 1, 6 on the dice to find out whether it's even. We can also again go back to our dice example. This is very similar to saying, what is the probability that I throw number below smaller or equal to 3? Yeah, so 1, 2, 3. 1, 6 plus 1, 6 plus 1, 6, 1 half. Yeah, so same principle.
If we consider that the rolling the dice is discrete problem, not the continuous one, or continual, shouldn't it be like the sum of those possibilities? And because
yes, exactly. Yeah, yeah. So.
Because I don't get it, like, why should we represent the discrete problem with continuous curve?
No. The throwing the dice, it's a discrete problem. It's something which we can do here very easily, and to calculate to get the probability. To get that the probability is 1/2 of throwing number 1, 2, or 3 is a similar problem that if we have now continuous world, this is not the number on the dice. This is the number on the thermometer. This is the number on my cell phone for the charge of my battery. Despite you might argue it's discrete because it only shows you the percentage with the whole numbers. But yeah, we are now in the continuous world. That's the world which we have for most of our measurements. Good. So if well, let's somehow try to draw this CDF, maybe point by point, and maybe we could have already started. What will be if this is the probability, then of course we should expect that the CDF will be 0 at some point, 1 at the other point. Yeah, we are not dealing with the numbers here. We actually do not care about how tall is this point in the reality. We care about how much will be the integral under the curve. So if we integrate the whole curve from -infinity to infinity, so we should get to the point 1. So we should at this point expect some sort of asymptotic behavior that we will be going towards 1, yeah, because we went through all possible values, temperature, what is the likelihood, what is the probability that the temperature here is below 10,000 degrees. Yeah, it's almost 1, yeah. Mathematically, practically, it's 1, and the same asymptote we should also expect on the other end, because, well, we are not ruling out the probability that the temperature here might be -10. Some window broke and or the heating broke. Okay, so what happens between that? Well, this curve will always be positive, so there is no tricks with changing the signs, like we have a positive surface area and negative surface area. No, this is all nice. Yeah, how do we know it's always positive? We draw it here. Yeah, this particular one is between 0 and 1, but it's without that constant square root 2 pi. Okay, so let's just now say we calculated the integral, and for our z1 we get the value here. What would it say? The probability that the temperature in this room is Z1 or less is 0.2, 20%. Yeah, here is on the right hand side we can already say something about probability. And good. So if this is the derivative. So if I'm plotting integral, then this curve is a derivative to that curve. So first we have the small slopes. The slopes increase. We get the maximum slope here, which means we get what? We get inflection point. Maybe I need to redraw this. Yeah, we should get something like this. Let me redraw this this blue dot. Would it work, or I just made it up? Let's say that we take our z2 to be equal to mu. So now we are trying to get this integral, including the previous one. Yeah, getting the area under half of this curve. Apparently, we need to get bigger number than the blue one, than the number we got for Z1. We increase the temperature, so we are already asking what is. We are already getting probability. Well, probably most likely somewhere around 1/2. That's like counting on one, two, three numbers on the dice. So this is our Z2. Similarly, we can find some point Z3. And that would be, yeah, again doing all this. Does it make a bit of sense?
Zipper has higher probability than
Yes.
than me.
No? Oh, well, yes. What does it mean? This point is telling us probability of measuring Z3 or anything below it. Very, very good question. Yes, yes. Please go ahead. It's a standard, let's say, mathematical definition of the distribution function. So it might be not that intuitive. What we actually would like to get is. What we actually would like to get to is something, let's say of this sort. So we have our probability distribution. Again, how do we get to the probability distribution? You will try it in your exercises. You basically just collect some data and you calculate you try to calculate the two parameters of this curve, which is mean and the variance or standard deviation. So let's say that we have our PDF. This is what we measured from this is what we obtained from the data. Yeah, we might have measured the standard example is like a height. So if we now take us as a population, we will
also basically calculate the exact value. Like, I mean, in the distribution, if we just choose the different borders of the integral.
Of the integral, yeah. Then?
For example, if we want, for example, exactly to tell the probability that here it's gonna be 25 degrees, let's say.
Mm-hmm.
Usually we got like
absolute error.
Absolute error of it. So we can choose like Z1 to be, for example, 25 plus
25. Mm-hmm.
25.1, for example, and Z2 to be 24.9.
Yeah. This is where we are heading exactly. Yeah, yeah.
And we just need to make sure that the borders are selected correctly.
Yeah, yeah. We are getting there. Let's maybe just try to, similar to throwing the dices. We can now take a ruler and try to measure the height of everybody in this room, and I don't know, maybe we will see, we will get like 3 people are 185 centimeters, 2 people are 180 centimeters, and another person is 170, and 1% is 190. And well, similarly to how we started to throwing the dice, we were not getting the uniform distribution. It was just our experience, what we expected, what we knew about. So we can then try fit, and you will try this in your exercises. Try to fit the normal distribution, because once we have it, then we are back to, so we get data. From the data we get mean, we get the standard deviation, because then we can start asking the questions that Adam already meant. No, thinner line. So let's say this is our mean. If it would be standard distribution, the mean would be 0. We can always discard some number to make our distribution standard. And now let's move and let's discard or add. This is what you meant, yeah? Discard or add some specific numbers, and we can discard like 1, 2, 3, and so on. In general, we can just try discarding this sigma here. In principle, oh sorry, no. If we look back here, our x and our sigma are somehow should somehow live in the same world, right? Because let's say if x is temperature, then in the numerator we get Kelvin squared, and in the denominator, such that it works out, we should get again Kelvin squared, and this Kelvin is only coming from the unit of the standard deviation. So we can then say, we can then take this standard deviation, it's a constant, yeah? So for our standard distribution, this will be -1, this will be 1, yeah? In case the standard deviation is equal to 1. But we can go even to more popular intervals like -2 standard deviations and +2 standard deviations. What we can now try to ask is exactly this thing. The height in our population in this classroom, the mean of it, let's say it's 176.1 through 192, whatever number. So who has this height? Nobody, yeah, because we got this number through some averaging, through some mean. But we can start asking, well, who has the height between 170 and maybe 180, 85? Which?
That's quite a big thing.
Well, difference. It's just an well, okay. So let's do it smaller. So 174 and 178. Yeah. Maybe we again do not find anybody, but at least we can calculate the probability. The probability of this is 0, yeah, because the integral is from the integral is on one point. It's the area under this point is actually 0. But this already starts making sense to ask these questions. So the standard or more usual way is to think about these sigma intervals. Some years ago, it used to be very popular that we were looking at the results from the CERN, whether the neutrinos will surpass the speed of light, whether the Higgs boson would be discovered. They call discovery if they measure something with plus minus 6 standard deviations, and let's see how big this probability is. So let's ask now the question: what is the probability that our x is between? I should write it. Our x is between its standard deviation minus 1 sigma and standard deviation, what is it, mu? Standard mean plus 1 standard deviation. We can again, I mean, this is very similar to what we already saw for the distribution function, and we can actually say, okay, let's just take the lower bound of this interval to be the start of our integral, and take the upper bound to be the upper limit of the integral. Let's take our PDF and let's do the integration. Let's say that we are in this world of standard distribution, which means that our mean is 0 and our standard deviation is 1. And let's try whether our MATLAB will come to the rescue again. Why does it need to connect so many times? Do you use it on tablet, the MATLAB? Don't do that.
It's doing it probably because you have it connected to the cloud, because Mathware has got like its own cloud, and usually all scripts you write there.
Yeah, but
There.
yeah, but I mean, I didn't go on a 1-week vacation before since the last time I used it. It was 20 minutes ago. Okay. Well, whatever. Good. So let's now do the integral. Now I have our function written here, so that we have it directly 1 over square root 2 times pi e to the and so on, and this is already the function where mu is equal to 0 and sigma is equal to 1. And what should we get? We get 0.6827. So the probability, what we just calculated, is actually not the case only for like one specific example. It's actually general. Once we would know the mean and most importantly the standard deviation, we can then say for any standard deviation, for any mean, the probability that our values, temperature in the room, height of the people in the room, will be between plus minus 1 standard deviation. Is 60. How much was it? 68.72? 27. Whoops. And we don't need to stop there. Sounds like relatively small probability. If we want to have to be like more certain, what probability would we like to have? 1 is impossible. So what is or 100% is impossible. What do we want? how much probability would you bet your life on your right hand on? Yeah. What's the probability that the plane crashes when you are loading it? Let's try at least to go with these values of sigma, just to increase them in multiples. So 2 sigma, or plus minus 2 standard deviation. Yes, some standard deviations away. Well, again reconnecting. Do we have it still? Yeah, let's just take the boundaries, change the boundaries of this integral. Not bad, yeah. Already 95 point something. 95.45% of the cases. So if we just ask, and well, maybe I draw this picture intentionally that way, it already starts to suggest this, that so the probability in this 1 sigma band, so plus minus 1 sigma plus 1 sigma, 68%. If we just extend, so 2 sigma, then already 95%. That's not bad, yeah. If you are designing a controller for the temperature in your room, maybe you don't care about the 5% of the cases when it will go wrong, yeah. So if you want to be even more certain, we can go to 3. How much do you expect? 98. Let's see. I should put 3 here. Not bad guesses. Let's see. 99, 98. Yeah, somewhere in between. So 99. What will be the good color? Let's say this one. 99.73, something like that. That's almost everything, yeah. And you will see if our certainty about certainty. If we say this is the mean height of the population and the standard deviation is 1 centimeter, that means that almost everybody in this room would be 1 centimeter would be that, okay, this will be like this 2 sigma interval, yeah, like 2 centimeters below 6, 2 centimeters above 6. So 95% people, almost everybody, will be between 174 and 178. So probably the standard deviation would be something slightly higher. Let's now see how we can calculate this from the data. Let's just do it quickly, so that if we collected some data points, x1, x2, xn. So the mu with this hat would actually mean our sampled mean, because we are not getting the exact exact mean value, but we based it only on some of our observations. This is the same thing why through ChatGPT you don't get the correct answer, but you get the answer that was found on the internet. Some of the answers checked by some people, and some of the answers even checked and answered by the experts. So ChatGPT is some mean sample, mean sampled from some population, and this is very easy thing which you might expect. Yeah, we do the average, arithmetic average. We sum together all the values and we divide by the number of the trials. Same as we did with our 1/6 probability of the dice. How to find the standard deviation, or let's say variance, that's more intuitive, is again going to be an average, but it's now the average of how our data points, not finished, so far so good, so far same, so how our samples are different from what we calculated in the line above, so from our mean. And since this difference can be positive or negative, this square comes to the rescue. So the standard deviation is average distance of like our heights in this room, the temperatures in this room throughout the year from its mean value. Unfortunately, this is the thing that ChatGPT cannot calculate, because for ChatGPT, like getting one of these samples is one training of 40 billion parameters, which consumes a couple of $1 million. So we would need to get at least a couple of trainings, and that's nobody gonna pay for. Okay, any questions to that? Good intro to the statistics. Was it too far from what you recalled? No? Okay. Oh, if it wasn't too far, then you should have chased me to be faster. Good. If no more questions, then thank you very much and see you next week.